Let's do part 2 of lab 21. So we'll start with lab part 2.1. So in part 2.1, we want to use several, and we aren't told what several is. We're trying to use several NAND gates to do the AND function. And the easiest way to do that, and maybe even the only obvious way, is so what you have at the output of a NAND gate is exactly what you want, except that it needs to be flipped, right? So, somehow, NAND, so you take NAND is A and B, the opposite of. So if we take the opposite of that, then you get A and B. So we just want to take this and logically invert it. And one way we turned a NAND gate into a logical inverter in the previous exercise was by running one input here and the other input to plus 5 volts. Oh, and this is a NAND. So that would work. But it's actually more convenient since these two inputs are right next to each other. It's a little bit more straightforward, and I would argue even a little less error prone to connect them like this. So basically, you take the output of this gate and put it together into the two inputs simultaneously to this gate. So that turns this into an inverter. So the symbol for an inverter is like that. So by connecting the two inputs of the NAND gate together, you've basically turned it into an inverter. So you take the output of the NAND, you invert it, and that gives you AND. Okay, so how did we wire that up? We set up our push buttons the same way we did in the previous exercise. I forgot these resistors at first, and I got some funny intermittent values, where the light would kind of respond to the button and then it would be sticky for several seconds. That was a funny and mysterious result because when I let go of the switch, the input was floating instead of being connected to ground. So that was a nice reminder of what I had just told you. So we have our two push button switches set up the same way they were a moment ago in the previous section of the lab. And then in these resistors, I think it doesn't matter too much what the value is, but all three of these resistors are 100 ohm resistors. They could be like 1K resistors, I think, and that would be just fine. So here are pins 1, 2, 3. So these are the two inputs and the output of this first NAND gate. And then here are pins 4, 5, 6. So the two inputs and the output of this second NAND gate. And then the output here goes through a resistor to a red LED so we can see the LED light up when the AND function is satisfied. And again, if you have A, B, and A and B, so let's say false, 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 true, false, true, false, false. So the only way you get A and B is if both of its inputs are true. So you can say false, or you can say low, and you can say true, or you can say high. Okay, so here's how it's wired up. Again, I'm using 5 volts. There's no plus 9. I'm just using 5 volts and ground. So the left side of this push button is connected to plus 5. The left side of this push button is connected to plus 5. The right side of this push button goes to the input pin 1 or 2 respectively. And then I have a 100 ohm pull down resistor. See, pull down resistor means like if nobody is affirmatively driving the line to one voltage or the other, then the pull down gently pulls it to, in this case, to ground. Pull down usually goes to ground. Pull up would go to like whatever your positive voltage is, like plus 5. okay, that's pins 1 and 2. So pins 1 and 2, they're connections to the right side of each switch, and then the pull-down resistors. Pin 3 is the output of that gate. So it just goes directly across to pin 4 using this little blue jumper, and then pin 4 goes to its neighbor, pin 5, with this other little blue jumper. And then this output goes with this 100 ohm resistor over to the top, the long leg of this red LED, and then the short leg of this red LED gets plugged into ground down here. And if I don't push either of these, it's off. If I push just one, it's off. If I push just the other, it's off. But if I push both at the same time, then it's on. Cool. Okay, so that looks like the AND function. Nice. Okay, so that was part 2.1. Okay, next for part 2.2, we want to combine several NAND gates from this 74HC00 chip to perform the OR function. So we can be formal here and use De Morgan's theorem. So let's see. So De Morgan's theorem says if you take A and B and you say, what makes A and B false, right? How do you make A and B be false? Well, A and B is false if A is false or if B is false. You know, it's raining and I have my umbrella is false if it's not raining or if I don't have my umbrella. Okay, so then you say, well, how do I make not A or not B? Well, yeah, so the opposite of A or, no, sorry, the opposite of A and B is not A or not B. Yeah. So this little thing usually means and this little thing usually means or in kind of formal mathematical logic language. And there are other ways to write it instead, which look more like C code, or you can write out A and D, you could write out OR. Okay, so A and B, the opposite of, is not A or not B. So then, if we simply replace A in this expression with not A, and replace B in this expression with not B, then we can replace A in this expression with not A, replace B in this expression with not B, and not A is A, not B is B. So A or B seems to be the NAND function applied to whose inputs are an inverted A and an inverted B. So that says if you take A, invert it, you take B, invert it, put those into a NAND gate, that gives you A or B. And that for that reason, it turns out people who like to draw little bubbles, a little bubble means logical inversion. So these are two different ways to draw a NAND gate. So this is actually are both a NAND gate. NAND. This is also NAND. So you take, see the AND function. So this thing typically represents and this thing typically represents, I don't know if it's typically, I think it's always. So this is and, this is or. And the only way I can remember this is that this thing has like a, you know, you shall not pass, you know, and then this thing is a little more easygoing. So I think you take the and, which is like, right, no, and then you take the or, and it's kind of like it bends a little more easily. So this, you have to have both things, or everything has to be true for this to say true, and this one, any one can be true, and this thing will say true. Okay. So then you put the little bubble here, that's NAND. But you can also say, well, let's turn it into an OR and put the bubbles on the input. And that's the same logic gate. And sometimes people sometimes people use the low voltage to represent true, and sometimes people use the high voltage to represent false. That's called active low logic. That's why it's kind of useful to distinguish high and low, which are the voltages, from true and false, which are supposed to be the intuitive meanings. So then the little bubbles convert active low into active high. So you see, so this is like, so a NAND gate with active high inputs is the same as an OR gate with active low inputs. That's pretty tricky. You don't have to follow that if you don't want to. Okay, then we know how to make an inverter. We just take a NAND gate and we tie both of its inputs to each other, and that gives us an inverter. So we're going to use now 3 parts of this 74HC00. So this first part we're using as an inverter. Yeah, so this is basically just an inverter. And this part we're using, oops, as an inverter. And then this part we're using as a NAND. Its normal function. So pins 1, 2, and 3 are our first inverter. Pins 4, 5, and 6 are our second inverter. And pins 9, 10, and 8 are our NAND here. So, and remember, so we just wire the 2 inputs to each other. That way, the output is just the opposite of these the shared pair of inputs. And then we have the switches wired up in the same way as we did just a moment ago. So in case you didn't believe me about De Morgan's theorem, let's walk through it step by step. A, B. Okay, let's invert each one. So we invert A, we invert B. Okay, that's good. Then you say, okay, now ignore this. Ignore this. So that doesn't work. So then if you take the AND of this column and this column, so it's only true if the inputs are both true. Okay, so there's true, false, false, false. Now invert what's in this column. Okay, so everything here is just the opposite of what's here. And you see, and then you say, okay, that is the NAND of what happens when I invert both of my inputs. And now let's compare that to straight, plain old OR. So here's A or B, false, true, true, true. And you notice these 2 columns are the same. So that's our simple-minded proof of this statement. Okay, now let's build it and give it a try. Okay, let's give this a try. So let me show you how I wired it up. So the left-hand switch, the left side of the left-hand switch goes up to +5. The left side of the right switch also goes up to +5. The right side of the left switch goes over with this blue wire to pin 1. And that pin 1 goes with a 100 ohm resistor down to ground. Then that pin 1 goes with a little blue jumper over to pin 2, so those 2 inputs are always seeing the same thing. We'll talk about pin 3 in a minute. Then the right side of the right switch goes with this little blue jumper over to pin 4. Pin 4 goes to pin 5 with this little blue jumper wire. And then we'll talk about pin 6 in a minute. And then pin 4 also goes down to ground with this 100 ohm resistor. So now pin 3 goes to pin 10. Here's 8, 9, 10. Pin 10 with this blue wire. And then pin 6 goes to pin 9 with this blue wire. And then pin 8 goes through this 100 ohm resistor to this column. And then that column goes to ground through this red LED with the long lead here and the short lead going to ground. And if I push the left button, the LED lights up. If I push no buttons, it's not lit up. If I push the right button, the LED lights up. And if I push both buttons at the same time, the LED lights up. So that seems to be the OR function. So we did indeed succeed at turning, in this case we needed 3 NAND gates. We turned 3 NAND gates into the OR function. So to make AND, we needed 2 NAND gates, and to make OR, we needed 3 NAND gates. Okay, so we did it. That was part 2.2. So I think now let's move on to part 3 in the next video.